Yesterday we started discussing splitting of Poisson process. The setting is that we have a Poisson process of rate lambda running, and you toss a coin every time there is an arrival independently each time, and if your coin shows head, you send the arrival up. If your coin shows tail, you send the arrival down, all right. This results in two counting processes, N1T and N2T. What we said is that for this IID Bernoulli, this is called IID Bernoulli splitting, okay, Bernoulli P split. We said that N1T and N2T are Poisson processes of rate lambda p and lambda 1 minus p respectively, and these two processes are independent. Okay. So, it is not surprising that the up process is of rate lambda p, because you are sending a fraction p of the arrivals up, and likewise the process down process is of rate lambda 1 minus p. What is surprising is that they are both Poisson processes, and even more remarkably that the two processes that result from the same process, splitting the same process, are in fact independent. Okay. That is a very remarkable property. Yesterday we showed this little o delta approach, right, to prove that the split processes have the correct distribution. You got the up process had they had a Poissoning IID Bernoulli sort of increments with parameter p lambda, right, and SIP and IIP would follow from SIP and IIP for the original process, and the fact that these Bernoulli splits are independent. Okay. So, this much we showed yesterday, we wrote it out and showed yesterday. What we cannot show using this this lambda delta approach is that these two processes are independent, that you cannot show, all right. So, the approach we took in the last lecture, this little o delta term makes all the difference. Okay. If you cannot this little o delta is essentially what induces this independence, as I argued yesterday, right, because if suppose in the original process you had one arrival with probability lambda delta and 0 arrivals with probability 1 minus lambda delta, all right, no little o delta involved. So, and the probability of having 2 or more arrivals is precisely 0. If this were the case, then you can show that if arrival went up in that micro slot, you cannot have a arrival in the down process, right, which means that these two processes cannot be independent, correct, because if I know something, if I know there is an arrival in the first process, there is no arrival in the second process, and they are not independent, right, correct. Now, because the probability of 2 or more arrivals at the same time is not exactly 0, it is close to 0, but it is not exactly 0. So, there is ever so small a probability that 2 arrivals can come at the same micro slot. This independence comes via that in some sense. Okay. So, but this lambda delta approach is not fine enough to give us this independence. You cannot prove it using this lambda delta or little o delta approach. Okay. So, for this we have to directly look at so we have to take a direct approach, all right. Basically we will use the Poisson PMF of NT. Okay. Now, the way we do this, so proof of 2, I indicated how 1 is proved. So, the lambda delta approach is okay to prove 1, not enough to prove 2. Okay. Proof of 2, you look at something like this. You look at the probability that n1 t equal to m and n2 t, you fix a t, okay, first, equal to n, given n t is equal to m plus n. You look at this conditional probability. Okay, you fix a t and you look at the probability, the conditional probability that given there has been m plus n arrivals in the original process, you are looking at the probability that m were sent up and n were sent down. What is this equal to? So, you've had m plus n, you are given that you've had m plus n arrivals in the original process. You are essentially looking at the probability that of these m plus, every time there is an arrival you toss a coin, right, and of these m plus n coin tosses you want exactly m heads and n tails, right. What is the probability of that? This is a binomial, right. So, this will be m plus n choose m p to the m, correct. This is true for all m n greater than or equal to 0 and t greater than 0, correct. Now, we also know, see, the n of t is a Poisson process. So, what is the probability that n of t equal to m plus n? This is m plus n factorial e power minus lambda t raised to m plus n, right, correct, because n t is a Poisson process. I know the Poisson PMF, right. So, I can write the joint distribution as, so if I look at this guy, probability that n1 t equal to m and n2 t equal to n, okay. This is just the product of these two, right, by definition of conditional probability, correct. So, I will get what, let me just write the m choose this guy as m plus n factorial over m factorial n factorial p to the m 1 minus p to the n lambda t. So, I will write it like this, lambda 2 to the m lambda 3 to the n over m plus n factorial, correct. What have I done? I have just written out this m plus this binomial term as in terms of these factorials, correct, and this lambda t to the m plus n I split it like this. I think I have missed a term. So, there should be e power minus lambda t, thank you, right. So, I can, so okay, this guy goes off, good thing, right, and then I can basically this p lambda t whole to the m. Now, I can basically I can marry this and this, I can marry this and that, right, they are all power m power n, right. So, I can just, so let me write this again, probability n1 t equal to m, n2 t equal to n will just be p lambda t to the m over m factorial. Then I can write, so this e power lambda t again I am going to split, okay, I am going to write it as e power minus lambda p t, okay, times 1 minus p, you see where I am going, right, 1 minus p lambda t to the n by n factorial e to the minus lambda 1 minus p t, correct. This e power minus lambda t I am just splitting into that times that, this is a Poisson PMF with parameter p lambda, right, correct. and likewise this is the Poisson PMF with parameter 1 minus p lambda, right. See, we have already shown that in the previous proof I already shown that N1T is a Poisson process of rate p lambda using the lambda delta technique, right. So, this Poisson PMF simply represents probability that N1T equals m, and likewise this represents N2T equal to n, right. This is true for all t greater than 0 and any m comma n non-negative integers, correct. So, what have I shown? I have just shown that the joint PMF of N1T and N2T factorizes. What does that mean? What and what are independent? N1T and N2T are independent for all t, right. Thus, the random variables N1T and N2T are independent for all t, correct. So, am I done proving independence of these two processes? I have proved it for all t, right. What have I proved? I have just finished proving that for all t the random variables N1T and N2T are independent. Is that enough to show that the two processes are independent? This is true for every t, right, but it is not enough to show that the two processes are independent, right. To show that the two processes are independent, you have to use we need to show that for all times 0 less than or equal to T1 less than T2 less than Tk, you want to show that N1 of Ti N2 of Tj are independent. Right, see, because just showing that N1T and N2T are independent random variables for every t is not enough. You have to prove that every finite collection of the N1Ts N1T1 N1T2 etc. is independent of any other finite collection of from the N2s, okay. See, what we have shown is that if I is equal to j, right, in these two indices, then I have shown that N1 Ti and N2 Ti are independent. So, for I equal to j, I can use whatever I have proved so far, right. So, for I equals j, independence is shown above. Now, for I not equal to j, now what do you have to use? If I look at N1 T1 and let us say N2 T2 or some other collection, right, what do I have to show? Right, I have to show that they are independent. Now, the original process has IIP, right. So, since the original process has IIP, I can use IIP of the original process to show IIP implies independence, IIP of NT can be used to show independence for I not equal to j, okay. You can write it out and see, okay, it is not a difficult thing to do, okay. So, that proves the part 2 of the statement, which is that these two Poisson processes are that come from the split are in fact independent Poisson processes, correct. Yeah. So, in some sense this Poisson process is very much like a Bernoulli process in almost all respects, except that when you split a Bernoulli process you do not get two independent processes, right. So, if you just take this Bernoulli example, let us say you have a, you know what a Bernoulli process is, right. So, time is, for a Bernoulli process time is split into discrete intervals, okay, and in each interval you have a array. So, this is like 0, 1, 2, 3, right, does not matter, it could be delta 2 delta, I do not care, right. So, Bernoulli process has an arrival with so probability q, no arrival with probability 1 minus q, okay, in each discrete time slot, okay, and these are independent across time slots, okay. So, here you have an arrival with, this is discrete time slots, okay, this is not continuous time. So, you have an arrival with probability q, here there may be no arrival, here there may be an arrival and so on, okay. Okay. Now, you split this guy with another Bernoulli coin toss which is independent of the process, okay. So, maybe this is a bad place to write all this. So, I am going to write the split here, right. I am going to split, this is Bernoulli q, right, this process is Bernoulli q, this process is this process is Bernoulli p. So, this again is a discrete time process, zero, 1, 2 and so on. Okay. So, this I am taking a Bernoulli process which is Bernoulli q and splitting with another Bernoulli process which is Bernoulli p, okay, and the splitting process and the arrival process, the original Bernoulli q process are independent, okay. So, here what will happen is that you can show that this is a process which is Bernoulli of what p q, right, because you have an arrival here, if and only if you had an arrival in the original process and your coin toss sent it up, correct, yeah, and likewise this down process will be Bernoulli p of p times, sorry, I think it is q times 1 minus p, right. The down process will be a Bernoulli process with arrival probability q times 1 minus p in any time slot, same logic, but what is the big difference? These two processes are dependent, yeah, is that clear? Because if I do see an arrival here, there cannot be an arrival here. So, given that this process conditioned on there being an arrival here, you know for a fact that there cannot be any arrival here, whereas if you split a Poisson process you get two Poisson processes which is nice, but what is even more remarkable is you get independent Poisson processes, okay, and this independence as you see, right, here there is just q or 1 minus q, right, there is no little o delta involved, and because of the little o delta which is that innocuous thing which is mostly a nuisance, right, is actually giving you this independence, right. So, let us not be, I mean let us show some respect to this little o delta, okay. So, it is very important, it is a crucial aspect of the Poisson process, okay. So, that finishes the module on splitting, okay.